This presentation will cover the three ancillary systems installed in the Corvette: cooling, power steering, and power brakes. Because the car is a convertible and I only plan to drive it in the summer, I do not plan to install the heating system and I do not plan to install the air conditioning system. The systems are essentially designed, and I do have space allocated for future installation if I so choose. This is a picture of the coolant flow as I've designed it for the electric Corvette. If you look at the bottom center of the diagram where it shows the radiator and fan, I use a carryover radiator and fan system, although I do control it differently. The coolant is discharged from the radiator at the lower connection. It goes to an electric water pump through a flow switch, through the motor, then the controller, then the charger DC to DC converter, through a flow sight indicator, and then back to the radiator slash fan system. I do have a fill tank and a vent that connects to the fill tank. So each one of these items I'll talk about briefly to explain further how they were connected to the system. The coolant flow is the same in both run mode and charge mode. The only difference is the fan does not run in run mode. It's not necessary, so it only runs when I'm charging the vehicle. So this is a picture of my electric water pump. It's positioned just after the lower exit of the radiator. This is a view looking down from above, and the line coming out of the radiator is 1.5 inches, and I have it reduced down to 3/4 inch going through the electric water pump and then discharging. The electric water pump is made by Bosch and is used in some European applications. This is a top view of the flow switch that is located just after the electric coolant pump. The flow switch has essentially just two positions. If no coolant is flowing, it reflects an open circuit. If coolant is flowing, it'll show 2.2 kiloohms of resistance. If for some reason while driving the car, if there is no coolant flow, then it would be a catastrophic failure given the situation where the motor and the Tesla inverter would overheat and be damaged. This is a circuit diagram of the coolant flow switch that turns on the check engine light on my instrument panel as a warning to me if for some reason the coolant pump stops working, and it'll allow me to avoid a catastrophic failure. This is a view of the instrument panel with the check engine light on as a result of no coolant flow to, again, aid me in visually seeing immediately when the coolant pump stopped working. So going back to the coolant flow diagram, on the left after the flow switch, the 3/4 inch coolant line is run through the passenger side rocker panel and goes to the motor, then the controller, and then to the charger DC converter. The way I've set up the plumbing is it enters each one of these devices on the low side inlet and exits on the high side as the outlet. After the coolant leaves the charger DC converter, it enters the driver's side rocker panel and goes back to the front of the vehicle on the driver's side. And the next step is to go through a flow sight indicator. This flow sight indicator gives me a good visual of how the coolant is flowing through the system. When it's flowing, the impeller turns and you can see how well the coolant is flowing by the rate at which that impeller is turning. I can tell you that as I'm initially filling up the system and trying to get the coolant to flow and getting the air out of the system, it does take a little bit of time, and that indicator is a good aid to help me understand when I have good fully functioning flow. So immediately after the flow sight indicator, the line tees and goes into the fill tank and then continues on to the top side inlet of the radiator, going from a 3/4 inch line to an 1.25 inch inlet line of the radiator. The fill tank was the original surge tank on the Corvette, but I've adapted it to be my source of entry for my coolant going into the system, and also the top of the radiator vents to that fill tank, allowing any air to escape out of the system. So here is a view on the driver's side of the vehicle showing the flow sight indicator and the coolant fill tank entering the radiator. The fill tank also serves as a reservoir, as it is the high point of the coolant system. So any air that's in the system escapes to the top of the fill tank. This is a view of the electro-hydraulic power steering pump made by Volvo. It's mounted to the backside of the front beam that the fascia attaches to. I essentially just have to run a 12-volt line that's capable of high amperage. I use an 80 amp fuse and I ground it. I also bought a circuit that's available to control the CAN bus line on the electric pump, and you can adjust the speed at which the pump runs. I use that and just run the pump at full speed. This is a view of the vacuum pump. It's a vane type that provides the vacuum to the vacuum brakes. It actually works very effectively and surprisingly quite quiet. So I've been very happy with this type of pump design, and therefore there's been no issues with the power brakes. This is a view of the vacuum pump for the power brakes next to the electro-hydraulic power steering pump made by Volvo. Both devices are mounted on the beam that's just in front of the radiator in which the fascia is mounted to.